In this video, I'd like to explore how you can get from Euler's method to the fundamental theorem of calculus in what I feel is a natural way, and a way that's not generally used by textbooks. So a quick overview. I always wanted the fundamental theorem to kind of flow naturally, maybe be an obvious result or close to an obvious result instead of this mystical theorem or technique that just came out of nowhere. And I, in the latter part of my career, use a problems-based approach to teach calculus. You don't have to do that to do this, but the idea here is that topics were explored simultaneously. So in this PowerPoint, you'll see that Riemann sums and the definite integral definition are going to be used in addition with Euler's method. Those topics are generally not taught in the same vicinity in a course, but they can be. And if they are, then this approach can be used. Okay, so one definition for the definite integral. If your function f is continuous, this can be used. If you define delta x to be the width of each equal subinterval, b minus a divided by n, then the limit as n goes to infinity of the summation from 0 to n minus 1 of f of a plus k delta x times delta x is one way to define the definite integral. I understand there are other ways to define it, and maybe this is not the most rigorous definition, but this is acceptable. And if you extend this to using f prime of x as your function, then you just naturally have what's here below. Same deal, except you just replace f with f prime. And that's important for what we're going to use with Euler's method. Now, Euler's method is a method to approximate a function value using a tangent line, in this case multiple tangent lines. So if we use a single tangent line approximation to approximate the value of this green dot here on this green curve, which happens to be natural log of x, then the tangent line, starting at 1, 0, goes off here, and you would get an approximation of 2 as the y value for the x value of 3, whereas down here you have a y value of 1.0986. The idea here is that you don't have a method to calculate the y values on the green curve without a calculator or without technology, but a tangent line, or any line, is very simple. You just need multiplication and addition to calculate y values. So 3, 2. Now we can say, okay, well 3, 2, this is not very close to this dot. It's not a very good approximation based on the picture. So if you can stop your linear approximation at some point during the interval, in this case we did it halfway, and then use a new linear approximation to take you the rest of the way, then this y value would be a better approximation to this y value than the original approximation. Okay, so that's Euler's method in a nutshell. If you write up Euler's method symbolically, this would be using 10 steps rather than the 2 steps. So here's a picture of the 10 steps. All right, you can see the 10 steps gives us a lot better approximation, a lot closer approximation than the 2 steps did, and definitely than the 1 step did. Okay, but again, each time we change course, we're using the slope of the tangent line at the x value chosen. All right, but if we write this up symbolically, then we have f of b, the y value we are interested in approximating, is approximately equal to where I started, plus the sum of the slope values, the f prime values, taking it at each x value, times the change in the x value. And the idea here is that this starts to look like, and is, a Riemann sum. And students, I think, naturally get curious, like, well, okay, 10 steps was better than 2 steps. 2 steps was better than 1 step. You know, can we just continue this process indefinitely? And so here's a little demonstration that students can play with. So right now you have a 2-step linear approximation or Euler approximation, and this slider lets you increase the number of steps. So I'm going to go from 2 to 8. So there's 8 steps. You can see this purple dot getting closer to the green dot. Let's go up to 16. And we're getting closer and closer and closer. You can click on this to see it's 1.1414, 1.0986 is the desired value we want. And if we continue this, then these connected line segments really start to look more and more like the green curve, right? So students naturally might say, okay, well, if we took, an infinite amount of these steps, then we probably would get to the actual y value that we're looking for. And that's kind of the natural extension of Euler's method that we would use here. So if you were to generalize what we're doing here, we're taking the value we like and saying it's approximately equal to the value where I start plus n steps of the slope times the change in x. And students would say, if I do this infinite number of times, or if we take the limiting value of this expression, then we should get the exact value for f of b. So in other words, if we take the limit of both sides of this, then we should change the approximately to an equality. That's maybe a little bit of a leap, and maybe you want more rigor than that, but I think students can accept that that's going to be the case. All right, so the limit of a constant, f of b is a constant. The limit of f of a, which is a constant, and then the limit as n goes to infinity of this is your definition of the definite integral, which we talked about earlier, except now f prime is your integrand instead of f. And here's your fundamental theorem that pops out of it. So that's a visual method, and I think a natural way to get from some concepts and techniques students know how to use to the fundamental theorem, which is the main beautiful result of Calculus 1.